Hello everyone. My poster is on characterizing the mechanical properties of ASTM A36 steel metallurgical phases using clustering analysis. We can utilize micromechanical properties of metals such as phase composition, hardness, and Young's modulus to quantify the macro scale material properties, which will allow us then to tailor some important design properties such as ductility and strength of metal. Our objective here is to simultaneously quantify the metallurgical phase volumes and the micromechanical properties of ASTM A36 steels using some clustering algorithms and the nanoindentation data. Um, we considered 7 ASTM A36 specimens for this analysis, 6 heat treated from various target temperature, and 1 specimen extracted from the as-received steel. On each specimen, we perform nano indentations over a grid of 15 by 15 with a spacing of 35 micrometer. On each nano indentation location, we developed a nano indentation load displacement curve, and from that curve, we extracted two important features, namely hardness and Young's modulus, which resulted in a master data set of size 1575 by 2. We then use this data set to construct two distinct data groups using K++ means clustering technique. We set the number of clusters to based on the fact that we have two metallurgical phases in our metal, namely ferrite and pearlite. We excluded Young's modulus as a descriptor from the analysis, as a preliminary analysis indicated its lack of discriminatory power. We then associated clusters to one of the metallurgical phases present in the metal by comparing the phase composition and hardness values with the existing literature. One of the important results we obtained in our analysis is the volume fractions. As you can see from this graph, the values ranged from 79% to 89% for ferrite and 11% to 21% for pearlite. In these graphs, plot between hardness and temperature and the Young's modulus and temperature, you can clearly see that our peerless is having higher values at all elevated temperature. However, the difference is not that significant in the case of Young's modulus. Also, you can see that the trend between ferrite and pearlite are almost similar in both the cases. We also plotted histogram and QQ plots to understand the distribution of these properties and found out that they roughly follow the normal distribution, but there are some deviations in the end quartiles. In the end, we compared the values we obtained in our analysis with the existing studies, and we found out that our values are in the similar range of what they reported. This graph shows the phase fraction we obtained in our analysis compared with the previous microstructural study. And clearly you can see that the phase fractions we obtained is in agreement with their findings. These are some of the references we used for this study. I would like to thank my advisor Dr. Ravikiran, my department, NDSU, and NSF EPSCOR for giving this wonderful opportunity. Thank you.